Hi everybody, this is lecture 14 of logical verification. I'm Rob Lewis, happy to be here. The topic for today is a formalization of the p-adic numbers in Lean. So the idea is you're going to learn a little bit of math, and you're going to see that that math has been formalized in Lean. The point really is nothing specific about the p-adic numbers. In some sense, this is a random bit of mathematics, no different from any other bit of mathematics. The moral is more that, well, these sorts of fairly complicated and important mathematical topics are not only possible to formalize in proof assistant, many of them have been. Lean has a huge library, mathlib, that has many results like this, many more complicated things defined in it. So it's possible, and it's done in practice. The motivation here, the broader motivation, is a project that we're running here at the FU called Lean Forward. This is a project that's aiming to verify modern results in number theory. Not just picking random bits of math from history, which the p-adic numbers kind of are, but we want to try to attack research-level mathematics. We don't just want to formalize the results and be done. We want to develop big, comprehensive libraries that contain many different results that allow us to build on them. And so the goal here, well, maybe we can kind of transform the way mathematics is practiced. Mathematicians don't have to review each other's papers anymore because they're formalized in Lean. Or if you want to look up a theorem and see what the side conditions are, what do you need to check to use this theorem, well, you just look in your database of formal mathematics, and everything is there, everything is spelled out, everything is known to be correct. In order to make this possible, you've seen in this course that formalization is not always easy. There are many challenges here. Well, we need to develop the system. We need to develop automation, not just generic stuff, but automated tools that really help with mathematics in particular. We need to learn what automation we actually need to make this possible. So there's a big research project here of trying to formalize mathematics, seeing what's missing, trying to fix that, formalize more, rinse and repeat, until we have revolutionized the field. So why number theory in particular? Well, there are some number theorists around who are interested in doing this. It also is a nice point between mathematics that's extremely abstract and mathematics that's very concrete. You might think of number theory as the study of numbers, like the integers, but it goes beyond this very quickly. Number theorists talk about, well, rational numbers, real numbers, but modularity, factoring. They do lots of inequality computations over all of these different kinds of numbers. They also deal with less familiar, more abstract number structures that might be less familiar as numbers even. Things called number fields, and what we'll talk about today, the p-adic numbers fall into this category. They're kind of like the real numbers, but not really. And then, well, okay, we also use many different kinds of polynomials. There's lots of algebra and geometry of these sets of polynomials. And then there are all kinds of fancy functions that we won't go into now. The point is that there's a lot to do. Some of it very abstract, some of it very concrete, and some things, like the p-adic numbers, at a nice point in the middle. Before we talk about the p-adic numbers, though, we have to talk about a general notion called a completion. So this is something that we can do to, we'll see first that we'll do it to the rational numbers, because the rational numbers are incomplete. What does this mean? Well, think about the rational numbers that are, the rational numbers x, such that x squared is less than 2, our first set on the screen here. And then think about another set, the rational numbers x, such that x squared is bigger than 2. Two perfectly reasonable sets of rational numbers, right? And in fact, every rational number is in one set or the other. Nothing's in both. So these kind of split the rational numbers in half, so to speak. The problem is both of them are open. If you draw them on the number line, you have one set over here, one set over here. They kind of meet at the middle, but there's no number there. There's no x such that x squared is equal to 2. So you kind of have what feels like a gap between these two sets. They touch, but they don't actually touch. Which, okay, there's nothing wrong with that, but it might be intuitively a little funny sounding. Another way to think about this, well, let's consider a sequence of rational numbers. Let's start with 1, we'll look at 1.4, 1.41, 1.414, and so on and so on. We're going to keep approximating the square root of 2 to a higher and higher degree. But we're always going to have a finite decimal number, so we'll always have a rational number. We'll never actually get to the square root of 2, and the square root of 2 is not a rational number. So these numbers they get more and more precisely approximating something, but that something is not a rational number. So again, it's nothing wrong, but maybe if you're a mathematician, maybe it's a little uncomfortable. Maybe it's not uncomfortable, maybe it makes you ask, well, okay, what can we do about it? And this is where the notion of a completion comes in. We're going to talk about a certain type of sequence of rational numbers, so a function from the natural numbers to the rationals. We call it a Cauchy sequence. And the property that makes a sequence a Cauchy sequence is that for every positive rational number epsilon, there's some index n, such that if we look at all of the numbers in our sequence beyond this index n, we ignore the first n and look at everything else, well, they don't really move around very much. They vary from the nth value by, at most, epsilon. The intuition here, a sequence is Cauchy if its entries eventually become arbitrarily close. So let's see what this looks like if we draw it. So a Cauchy sequence should look something like this. I'm going to draw the entries in red on this first graph up here. We said that eventually the entries have to get arbitrarily close together, which means that it doesn't really matter what happens at the beginning. Here I'm just drawing different values as we move right along the number lines. The first values kind of jump around as much as we want, but eventually they need to get closer and closer to each other. So maybe we see something like this. And after a certain point, well, they really can't move much at all. They have to become almost like a straight line. So eventually, as we move to the right down our number line, the numbers get close. How do we read this in this formal quantified statement? Well, let's try to take a look at that. Basically, what this statement says is that I give you some value epsilon, and that value epsilon is like a bound. It tells me, or it tells you, rather, how close you want to force the entries far to the right to be. So maybe I give you a big epsilon. It's like something like this. Well, you can say if I draw one line like that, didn't quite get that, one line like that, well, after that point there, everything to the right of this vertical line falls in this epsilon neighborhood. And here we're thinking of the height here as being a value epsilon. So that works for some particular epsilon. Maybe this epsilon was 10, and I don't really care what the value is. But then, the same thing has to hold if I give you a smaller epsilon. So what if I give you an epsilon like, I don't know, like 1/10, let's say. Erase all these guys. they give you a value like 1/10. You have to say, where can I draw a window whose height is 1/10 that captures everything after a certain point? And maybe it's like here-ish. Not really drawn to scale. But if I draw something like this, and I draw something like that, well, again, a little bit off. But now, maybe after this point here, everything to the right of my line is once again within this epsilon window. And I can keep shrinking the window over here. I might have to move it up and down a little bit, but I can always place it somewhere, no matter how narrow it is. I can place it somewhere that captures every point in the tail of the sequence. And this is what makes this sequence a Cauchy sequence. So there's another definition that we saw in our slides that said two Cauchy sequences are equivalent if for every epsilon there is an n such that if we look past the initial n elements of the sequence, then every element of S is within epsilon of the corresponding element of T. So here we again need to draw two different Cauchy sequences. So let's say our first Cauchy sequence is doing something like this. It's jumping around a lot, but it's sort of leveling out there. No, it's not a very good leveling out, but we'll pretend. Let's do another one. Let's do this one in green. So here's a sequence that, again, at the beginning is jumping around. Doesn't really matter what it's doing here. Maybe it even drops like this. But then, towards the end, it should approach the same values as the one in red. So if, again, I put an epsilon window like I did up here in blue, and maybe I want this one to be, maybe somewhere like this. So for whatever value of epsilon this height is, well, all the red dots after a certain point are within this window, and all the green dots after a certain point are within this window. After that point, just like here-ish, they never escape. So that means that these two sequences are equivalent. We can say that equivalent sequences, in effect, approach the same value. They get arbitrarily close to each other. You need to be a little careful about the phrasing approach the same value. Okay. So back to our slides here. So yeah, two sequences are equivalent if they eventually become arbitrarily close to each other. So our example from before, we had this sequence of rational numbers that was approaching the square root of 2, but, well, that's not a rational number. I at least claim that that sequence is Cauchy. And why is that? Well, let's think of my epsilon choices as being 1 over 10, 1 over 100, 1 over 1,000, etc. You give me any window like that. You say, I want to know that the sequence, the values of the sequence after a certain point are all within 1/10,000th of each other. Well, I just need to count the right number of decimal points and say, okay, I cut off the first 5 or whatever. After that, well, the first 3, 4, 5, if I cut off these, then everything that follows, the first 5 digits, are all the same. So everything that follows this point differs from this value by at most 0.000001. If I want more precision, I can go further to the right. I can add more zeros to that. So the entries are becoming arbitrarily close. which is exactly what we wanted from our Cauchy sequences. Okay, so why are we talking about this at all? What is this weird notion of a Cauchy sequence? Well, when we think about the rational numbers, we find these gaps. Filling in the gaps is supposed to give us the real numbers. It's really everything in that number line. In order to fill in the gaps, just kind of a metaphor, right? We need to know how to identify the gaps. And this is exactly what Cauchy sequences do. We can have a Cauchy sequence, like on the last slide, approaching the square root of 2. None of the values in that sequence is actually the square root of 2, but the sequence itself kind of picks out this missing value in the rational numbers. So Cauchy sequences identify the missing points. We can say that the set of real numbers is the set of all Cauchy sequences. Or can we? There's a little problem here. Some Cauchy sequences identify the same points. Our example was picking out the square root of 2, but we had the sequence that was kind of approximating the square root of 2 from below. We'd have another sequence that approximates the square root of 2 from above. They both pick out the square root of 2, but they're different sequences. So if I said that the real numbers were just Cauchy sequences with nothing else, I would have multiple copies of the square root of 2 in my set of real numbers, and that would not be what we were looking for. So we need to do a little more work. We're going to use a tool called a quotient. I'm sure you've seen this definition at some point in this class. A binary relation is called an equivalence relation if it's reflexive, symmetric, and transitive. Essentially, an equivalence relation allows us to take a set of elements and partition that set, to carve it into separate pieces, where all of the elements of the set in one of those pieces are equivalent to each other. So we can group the elements into different classes using this notion of equivalence. We call this an equivalence class. If I have a set, I have an equivalence relation on that set. I can look at the set of all equivalence classes of this original set. So basically what I'm saying is take my original set, partition it in this way, carve out the different equivalence classes, and then just pretend that each one of those partitions is one thing on its own. It's actually a set with a bunch of stuff in it, but just pretend that that is one cluster of stuff. It's one object. And look at all the different objects that I get. We call this the quotient of our original set with respect to that equivalence relation. So here's our notion of equivalence for Cauchy sequences. You might guess from the name that equivalence is actually an equivalence relation, and I'm going to leave this as an exercise for you to check yourself. But okay, if it's an equivalence relation, then we can take the quotient of the set of Cauchy sequences with respect to this equivalence relation. So I can say I had those two Cauchy sequences that were both approximating the square root of 2. It turns out that those are equivalent to each other. They approach the same value, so to speak. They eventually get arbitrarily close. So they fall in the same equivalence class, which means when I take the quotient, I don't have both of those elements floating around. I only have the one class of all the Cauchy sequences that are equivalent to those two. And that is going to be our real number, square root of 2. The set of real numbers is the quotient of the set of rational Cauchy sequences with respect to the notion of equivalence that we defined before. And this is what we call the completion of the rational numbers. So once we've done this, once we've defined the data that goes into the real numbers, the data of a real number is an equivalence class of Cauchy sequences. Then we need to show that we can add them and multiply them and do all the things that we'd expect to. Well, Okay. We can add sequences together just by adding things pairwise. And it turns out that if I have two Cauchy sequences, R1 and S1, I have two more Cauchy sequences, R2 and S2, that are equivalent to R1 and S1. Well, then adding R1 and S1 gives me something that's equivalent to R2 plus S2. So that's convenient. This is enough for us to define an addition on the quotient on the reals. And similarly for multiplication, etc. We're not going to worry about the details too much right now. But now we have a big question. Just explained how to get the real numbers by taking the completion of the rational numbers. But think about this in terms of programming for a second. What I've just described so far had some things hard-coded that didn't need to be hard-coded. We could have made some more things parametric. We could have made some more things be like environment variables or something like that when we did this process. And maybe we wouldn't get exactly the real numbers at the end, but the same algorithm would effectively work. Completion is kind of like an algorithm. So what did I hard-code unnecessarily? What can we possibly abstract? This is a question to think about for a minute. So, one thing that I often hear when I ask this question, people pick up on, well, the notion of a Cauchy sequence was a function from the natural numbers to the rational numbers, but why did we have to choose the rational numbers? Couldn't I look at Cauchy sequences of, I don't know, integers, some arbitrary type? Couldn't I parameterize the target type of the sequence? The answer is yes, you can. So a perfectly good notion of a Cauchy sequence. This gives you the completion of, rather than the rational numbers, some arbitrary type, anything that supports an absolute value. So if you thought that, very good. You're thinking, well, that's actually not the direction I want to go in now, though. There are other things we can generalize, too. Because I'm interested in the p-adic numbers, I want to look at generalizing the measure of distance that we used in the definition of a Cauchy sequence. So we have our function, our sequence from the natural numbers to the rationals, and we said it's Cauchy if blah, 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 the absolute value of Sn minus Sk is less than epsilon. Let's change that. We're going to say our sequence is Cauchy if blah, 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 nothing's changed. Here I've written abs instead of the absolute value. Well, what is abs? I don't know, it's respect to an absolute value abs. What is an absolute value, even? So the general notion of an absolute value, and this is not the standard, if x is positive, then x, else negative x, absolute value. This is supposed to be a generalization of that. The function is a generic absolute value if it has these three properties down here. And, okay, you can check that the normal familiar absolute value has all these properties. The only thing that has absolute value of 0 is 0. Sure. Otherwise it's positive. Makes sense. If I take the absolute value of two things added together, I can't get something huge. It's at most the absolute value of the two things added together. And, well, it's nice when you multiply things. The absolute value of a product is the product of the absolute values. These aren't very restrictive requirements. There are lots of functions that will satisfy this, we'll see. But in particular, the normal absolute value does. Think about for a second if you can find another function that satisfies these properties. I mentioned that, yes, we can also generalize the base type Q. We're not going to do that for now. Here's an example of a generic absolute value that's not the normal absolute value. What about the function that is 0 when the input is 0 and 1 otherwise? check for yourself that it satisfies these three properties. Not very hard to check. And it's a pretty dumb measure of size. An absolute value usually measures the size of the input. And this isn't a particularly useful notion, but it works. It's a valid absolute value. So this gives us all the machinery that we're going to need to talk about the p-adic norm. P-adic norm is an alternate absolute value for the rational numbers. But I've been talking about math for so long without seeing any lean code in a class about formal verification. So let's take a little break and let's actually see how all of what I've said so far is implemented in MATLAB. So let's hop over to MATLAB for a second. And I'm looking at the file in the data real directory called coseq.lean. And I actually don't think there's a ton to show off in this file because it very much says in lean exactly what I've just told you in my slides. So what is the notion of a Cauchy sequence? Well, first we need to know what an absolute value is. And okay, this is a type class in lean that says basically the same properties that I showed you on the slide informally. We'll go ahead, notice that it's actually slightly different but equivalent, and I think you can convince yourself that these are the same. I've just changed the condition that says, changed the phrasing of the condition that says the absolute value is only 0 when the input is 0. We'll prove some basic facts about absolute values, nothing so interesting here. Here, we'll define what a Cauchy sequence is. Well, a Cauchy sequence applies to any linear ordered field alpha. So remember I said that we could generalize the base type from the rational numbers to anything with the right algebraic structure. Well, here we are. We have any base type alpha that's a linear ordered field. Oh no, I'm sorry. Alpha is not the base type. Alpha is the target of the absolute value. So the absolute value function will take values in some linear ordered field alpha. Beta, the ring beta, is our base type. Ring meaning that we can add and subtract and multiply elements. I have an absolute value function, which goes from beta to alpha. And this is a predicate that's applying to a function f. So here we're saying that the sequence f is a Cauchy sequence with respect to the absolute value function abv. And the statement of this predicate is exactly what we saw on the slide. It says for every epsilon, and what is epsilon? You'll be able to see that epsilon is a, here we go, this is the context. Epsilon is an element of alpha. So for any epsilon in alpha, which is the rational numbers for us, there is some index I, which is a natural number for all bigger j's. Then the absolute value of f of j minus f of I, which is a value in alpha, is less than epsilon. So exactly the condition that we had before. Notice that this is, again, a predicate on the sequence f. This will become important in a sec. Okay, we can rephrase the notion of Cauchy in various ways. It's maybe a little interesting mathematically, but we won't worry ourselves too much. Here we're going to define the bundled type of Cauchy sequences. Nothing too complicated here either. This is just a subtype. So we're going to take the set of all Cauchy, the type of Cauchy sequences as a subtype of the type of sequences. We'll go ahead and define a bunch of things. Eventually, we'll have to define our notion of equivalent. Now this is phrased maybe not quite as it was in the slides, but it's really saying the same thing. When we say that the type of Cauchy sequences is a setoid, that means it has an equivalence relation on it, and our equivalence relation is lim0 f minus g. Read the definition of lim0 by yourselves, and you'll see that this is exactly what we had written on the slide. saying that f and g are eventually arbitrarily close. And then after that, we prove some things like if I add two equivalent Cauchy sequences together, I get something equivalent. We mentioned that as well. Same for negation, for multiplication, it'll all follow here. And then this file kind of ends. Do some things with orders, less than or equal to, on Cauchy sequences, but kind of peters out because the next step, which is not much of a step, happens in a different file called coseq completion. Same directory. Here we define the type big C Cauchy to be the quotient of the type of Cauchy sequences with respect to that equivalence relation that we defined. And that's all it takes. If we have any alpha and beta that instantiate the right type classes and some absolute value ABV, we can define this type Cauchy. We instantiate alpha and beta to both be the rational numbers, and we'll eventually define the real numbers to just be Cauchy with the right inputs. So really all the hard work is done for us. The big question is, what else can we do with this? Presented it as infrastructure for defining the real numbers. But we have parameters, right? We've done this as good computer scientists. We've generalized as much as we can. So what else can I plug in for alpha and beta and ABV? If we plug in a different absolute value, we get the p-adic numbers, and this is the topic of the second half of this lecture.